Hello, welcome to the last class of MAT 1350. So maybe not surprisingly, there is no time for the full story of Taylor expansions. So I want to just at least touch on it, just say what it is. And probably it fits with the theme of this class, because this whole class is not about what we've done, it's about what we haven't done. There's so much more in basically every direction we went, we've cut short, at the beginning, not even halfway through. So that one will be cut short too. Sorry. So let me remind you where we were. We actually had 6 groups of braids and 1 extra group, and I want to quickly remind you what they were. And and even here there will be lots of stuff that I will not be saying. So the extra group is the symmetric group. So I'm writing all the groups without indices, so without the number of strands, okay? So the symmetric group is just the group generated by tau I, where tau I are the transpositions, and under the relation tau I, the square of a transposition is 1. The transpositions satisfy this funny relation here, and 2 transpositions commute if they are far away from each other. That's the symmetric group. Then we define the braid group, and the braid group was the group generated by gamma I, where gamma I is the crossing of strand I with strand I plus 1, modulo essentially the same relations, except the relation tau, except the square is not equal to 1. And then there was the pure braid group, which was, so there is a map from the braid group to the symmetric group, basically by mapping gamma I to tau I, and the kernel by mapping gamma I to tau I, and the kernel of this map is the pure braid group. Okay? And we never have shown how to present the pure braid group as generators modulo relations, and in fact it's kind of ugly. There are generators and relations. The generators are fun, but the relations are kind of ugly. Sorry. But we haven't done that. Then we started generalizing this group. So we actually generalized this by making a mistake. So we wrote what might have been another presentation for braids, but it wasn't, and in fact it was a presentation of a new group called the pure virtual braid group. And then there was a quotient of it, which we call the pure W braid group. And then last class I mentioned that sort of virtual things come from having like knot diagrams which are not necessarily planar. Okay? And then when you change your mind, and instead of talking about knots, you talk about braids, then you're talking about braid diagrams which are not necessarily planar. And the meaning of it is really that if you have 2 strands, so if you have a braid and you have strand I and strand J, you can say, let J cross under strand I, even if they're not adjacent. So you define a generator sigma ij, which means strand J goes to strand I, crosses under and comes back to place, even if they're not adjacent. But it does it without crossing the strands on the way. So it does it by crossing all the strands on the way virtually. In other words, it doesn't cross them. Okay? So that's precisely what PVB is. Okay? And then it leads to saying, so let's think about the impure version of this. So the impure version of this will be the group generated by two types of crossings, namely the honest crossings and the virtual crossings. So it's really the Braid group, free product, the symmetric group, where the symmetric group stands for the virtual crossings and the Braid group stands for the honest crossings, modulus some extra relations which say that the virtual crossings don't really exist. You can move them around. Okay? And likewise, there is the W quotient of that. And if I had more time, I would have told you how how everything maps into everything else. Basically, how virtual braids map into here. I kind of just told you. I just told you sigma ij goes to the combination shown here of virtual and regular crossings. But then one has to verify that it actually works. Likewise for W braids, and I would have told you a lot more, and I would have told you that unlike in the case of ordinary braids, where the braids are actually not a semi-direct product of pure braids with the symmetric group, in the virtual case they are. In the virtual and in the W case, the impure version really is a semi-direct product of the pure version with the symmetric group in both these cases, and this means that you know, in classical braids there is a case to say that this group is the more interesting one, or at least that the two groups are interesting. In the W case, the moment you've understood the pure version, the impure version is just a semi-direct product of it. It's a trivial extension in a sense. So you know, if you're asking me, I like to study this group and that one and that one and that one, and I don't care about these two. And one last thing, so all these groups make a diagram as I have written here. So, you know, maybe the diagram is so, well, it's such in large scale that it's a bit hard to see, but really all the pure versions map into the impure version, and there is also a map of U goes to V goes to W. And one thing that it means is that if you have a good invariant of things here, then it will extend to an invariant of things here. Because this is just a semi-direct product, you'll have to figure out how the symmetric group acts on the invariant, and you'll be able to extend. And then usual braids map into W braids, so you'll get an invariant of usual braids. And if you have an invariant of usual braids, which by luck satisfies the Markov moves, you get an invariant of links. So why am I telling you this? Because today I will tell you a little bit about an invariant of PWB, which has all these good properties and leads to an invariant of links, and it's in fact the so-called Alexander polynomial, and I'll have nothing, you know, it's so disappointing, but I need, you know, another semester to say more about it. Anyway, sorry, up until now, okay, you know what, if you didn't follow anything in the last 10 minutes, then I hope you tuned out and daydreamed and had fun, but please tune back in, because now I have a fresh story to tell. I'm starting from scratch. Okay? So I want to tell you about Taylor expansions for groups, and I will also tell you, well, I mean, let's put it in quotes, and I will also tell you that PWB actually has a Taylor expansion, unique Taylor expansion, and that Taylor expansion, when you well, leads to the Alexander polynomial. Okay, so what's a Taylor expansion for a group? So let's start from a group. So let G be a group. And I mean any group whatsoever. I don't care what. Then let QG be the group ring of G. So the group ring of G is the collection of all formal linear combinations, so some AI, GI, finite. If the group is infinite, I still want the sums to be finite. Where AI are rational numbers and GI are elements of the group. And you extend the group multiplication to a multiplication on the group ring. And of course the group ring has addition. So this is a ring, and hence the name, the group ring. Okay? Now this ring has a famous ideal, so let I be the augmentation ideal, the augmentation ideal in QG. So I is the collection of all elements of QG. So all elements of the form sum AI GI, which have the additional property that the sum of the coefficients is equal to 0. So sum AI is equal to 0. You can check that you can check, I'm trying, maybe I shouldn't be doing this. I'm trying to move this. Okay. You can check that this is generated as a linear space. So this is the vector space generated by differences of elements of the group. So basically G1 minus G2, where G1 and G2 are both elements of the group. So clearly differences of elements of the group are in the augmentation ideal, because the sum of the coefficients are, well, the coefficients are 1 and minus 1, so the sum is 0. And you can check that you can write anything like this as a linear combination of differences. And in fact, you can also check that as an ideal. So as an ideal, it is the ideal generated by differences with 1. So G minus 1, where G is an element of the group. Well, basically, if you multiply G minus 1 to the left by something, you get G1 minus G2. Okay? Good. Now, whenever you have an ideal, sorry, I'm going to do something insanely abstract right now. And a moment later I will unwrap it and you'll see that I'm talking about Taylor series. Okay? So, whenever you have an ideal in a group, you can look at powers of this ideal. Sorry, in a ring. So, by definition, the 0th power is the full ring. Then the first power is just the ideal itself, so it's a subset of the 0th power. Now, if you take the ideal and multiply it by itself, so look at all products of two elements where both of them live in the ideal, so well, this is just the ideal squared, and it's a smaller set, because, well, the property of an ideal is that if you multiply something, well, if you have something in I and you multiply it by anything, you get something again in I. So this is clearly a subset of I. So you get a subset here. And then you can continue. If you look at the ideal cubed, it's an even smaller subset. And if you look at the ideal to the 4th, it's an even smaller subset, and it continues. So by the way, this thing where you have a vector space and a descending sequence of subspaces is called a filtration of the vector space, but I don't think we need it today. So anyway, let's define calligraphic A of G to be the infinite product as m goes from 0 to infinity of I to the 0, sorry, of I to the m divided by I to the m plus 1. Okay? And then definition. So, oh, sorry, I should have been even before the definition. I claim that this is also a ring, or also an algebra. It's called the associated graded of the original ring, and it's also a ring. Why? Because I just need to tell you how to multiply two things. So if you have, and in fact it's a graded ring. So this is a graded ring. So the degree m piece, or something is a degree in degree m, if it falls in the mth summand. So if it falls in I to the m divided by I to the m plus 1. So I need to show you how to multiply the equivalent class of A, where A belongs to I to the k, with, so this is an equivalence class modulo I to the k plus 1, how to multiply it with the equivalent class of B, where B is in I to the L, and this is an equivalence class modulo I to the L plus 1. Well, it's exactly what you expect. You take the equivalence class of this, of A times B, modulo I to the, so okay, if A is in I to the k and B is in I to the L, then A times B is in I to the k plus L. And then you take its equivalence class, modulo I to the k plus L plus 1, and you can check that this is well defined. And it's a trivial check. I'm not going to do it, not because, not even because I'm in a hurry, but because it's trivial. It's easy. You can do it. Okay, good. So this is a graded ring. And now I can make a definition. So, definition, an expansion for a group G is a linear map Z, which goes from the group G into its A, so into its, this is actually sometimes called the associated graded of G. So it's a linear map that goes from G to its associated graded, which has the property such that if A is any element in I to the n, I used m before, so I'll use m again, then, okay, first of all, if you have a map from Z, a linear map from Z to A of G, then you can automatically extend it to QG, to the group ring. You just extend it linearly. And then the augmentation ideal is, well, an element in the augmentation ideal to the M is in particular an element in the group ring. So you can compute Z of A. And Z of A lives inside this infinite product. Now, this is, so in other words, it's an infinite sequence of elements, each of which is in the corresponding quotient. So, Z of A should be an infinite sequence of elements. And the condition is that this infinite sequence will be 0, 0, and so on, up to degree m minus 1. In degree m minus 1, you get the equivalence class of A, right? Because A is in I to the m, the equivalence class of A will be in I to the m modulo I to the m plus 1, and that's the degree m piece. And after that, I don't care what you get. So after that, you get whatever you want. Anyway, that's the condition. Okay, why should you care about that? Let me give you two reasons. Okay, one reason is that it should vaguely remind you of what we call universal finite type invariants. And in fact, I will argue later that this is a universal finite type invariant for a group. And the group could be anything, but in particular, it could be a braid group, but it doesn't have to be a braid group. There is a notion of universal finite type invariant for any group, and I've just told you what it is. Okay? And the other thing that I wanted to show is actually different. Okay? So here is an aside. So let's do the same, but for a different ring. So a ring which is not a group ring. Okay? So take the ring R to be C infinity of R to the, you know what, let's make it D so that I don't get confused between M and N. So C infinity functions on R to the D. Okay? And for the ideal, I will not take the augmentation ideal, but I'll take something similar. So I'll take those functions in C infinity of Rd, which have the property that f of 0 is equal to 0. Okay? Then, what is, so now I want to figure out what's the corresponding construction in this case. So what is, what is I to the m divided by I to the m plus 1? So maybe first of all, what is I to the m? So I is functions that vanish at 0. So if you take m functions that vanish at 0, you get functions that vanish m times at 0. Okay? So you get, so these are functions with a 0 of order m at 0. So, okay? And then what is I to the m divided by I to the m plus 1. So if you look, so these are exactly homogeneous polynomials of degree m, right? Because if you're looking at if you're looking at functions that vanish m times, then their germs, so right near 0, they look like polynomials of degree m or greater. And then I mod out by things that look like the polynomials of degree m plus 1 of later or more. So these are polynomials, or sorry, homogeneous polynomials. So homogeneous polynomials of degree m. Okay, and then what is A? So A of this ring. So A of this ring is the product of all homogeneous polynomials of all degrees. So this is exactly power series around 0. I mean, everything is happening at 0. So around 0. And then you can ask, so suppose now I'm looking for a map Z from R to A of R. So in our case, this is a map Z from C infinity functions. Let me not write on where. From C infinity functions into power series. And it should satisfy some property. Okay? I will not write the property right now, but you can guess. Sorry, I need a little more space. You can guess. I mean, one map like this comes to mind immediately, and it's the Taylor expansion. So I don't know. Let me call it homework, but I don't. It's not for submission, of course. Verify that the Taylor expansion. So this is a map from C infinity functions into power series, has the required property. So is an expansion. Okay, it is actually far from unique, but I can make more I can insist on more properties that will make it unique. So two more properties are as follows. So property 1, I will call an expansion. So an expansion is homomorphic if, so you see, if you add an additional property. So an expansion is a map from G into A of G, and G is a group and A of G is an algebra. So both have multiplication, or this is a ring. So both have a multiplication. And you can ask that the expansion will be multiplicative. So if this map is multiplicative, so the corresponding property of Taylor expansions is the fact that the Taylor expansion of a product of two functions is the product of their Taylor expansions. Okay? And then there is a harder to describe property. So this whole construction that we made is actually functorial. So if you have a map from G to H, then it induces a map from A of G to A of H. In particular, there is always a map from G into G cross G, and this is the so-called diagonal map. It's the map that maps every element lowercase g into the ordered pair G comma itself. Okay? So this induces a map from A of G into A of G cross G, and it is non-trivial, but nevertheless true, that that this is the tensor product of A of G with itself. So this is A of G tensor A of G. Okay? And then the property that you could insist on is, so actually maybe I should have given these maps a name. So this map is called delta. And let's call this map also delta, and it's a coproduct. So you can insist on a second property, that Z will be co-multiplicative. So an expansion is called co-homomorphic if this map is co-multiplicative. If Z is also co-multiplicative, meaning if the diagram that I'm writing now is commutative. So this is the coproduct, this is the induced coproduct, this is Z, and this is Z tensor Z. So it is co-homomorphism if this is co-multiplicative. So now another homework assignment, which again, sorry, this is the last class. I have 17 minutes. There's no way I can go through everything I want to go through. But another homework assignment is homework. So maybe it's 2. So the Taylor expansion, is both homomorphic and co-homomorphic. And the second property, and part 3 is, it is the only thing with that property. So any expansion from C infinity into power series, which is both homomorphic and co-homomorphic, is the Taylor expansion. So the okay, the moral of all of this is that the Taylor expansion has an algebraic characterization, and furthermore, this characterization makes sense for arbitrary groups. Okay? So hence one is curious. I don't know if it's useful or not, but it should at least arouse. No, I don't know. Curiosity which groups have Taylor expansions. So one is curious which groups have Taylor expansions. And you know, you can go through lots and lots of lists, and some groups do, some groups don't. But I want to tell you about one that does, and this is PWB. Okay? But before that, I want to relate, so I said a Taylor expansion looks like a universal finite type invariant. I want to make it a little bit more precise. Okay? So consider, for example, braids. Okay? So let's take the group G. Let's take the group G to be the pure braid group. Okay? So for the pure braid group, so okay, I mean the elements of the group, so the elements of the group ring look like linear combinations of braids that induce the identity permutation. Sorry, that wasn't a very creative braid, but linear combinations of such. The augmentation ideal is generated by differences of braids, right? But if you have a difference, right, because it's always generated by differences of braids that induce the identity, the same permutation, the identity permutation. If you have a difference of two braids, you can get from one to the other by a sequence of crossing flips. And each crossing flip is a difference between two braids in which you flipped one crossing to be between overcrossing and an undercrossing. So I is generated by braids that have a single double point, which is interpreted as an overcrossing minus an undercrossing in precisely the Vasiliev sense. And when I say generated, I mean you are allowed to take linear combinations of things like that, and you're also allowed to multiply things like that by other braids. So in other words, this double point appears in a bigger context. Okay? Now, I to the m is similarly generated by braids just like ordinary braids, but that have m double points. Okay? So this is exactly analogous to the analysis we did for knot theory. And in fact, so linear functionals on on the group ring which vanish on I to the m+1 are finite type invariants for braids. I mean, this is exactly analogous to the analogy to the analysis that we did for knots. And in particular, the conclusion is that A of G, well, it's not quite the conclusion, but A of G is analyzed in a similar way, and it comes to be chord diagrams. But what kind of chord diagrams? So you see, in a braid, crossings are always are at the same height. Like the skeleton is parametrized. The skeleton is parametrized, say, between 0 and 1. And when two things cross, they are at the same height. So a chord would stand for a double point between strand 1 and strand 3, but the chord has to be horizontal because the only crossings that we are allowed are equal height crossings. So there will be A of G will be generated by chord diagrams that have a number of horizontal chords. Modulo relations. I could write the relations. In fact, why don't I write the relations? The most interesting relation, the only relation, in fact. So the relations are the only interesting relation, in a sense, is the four-term relation. The four-term relation is exactly the four-term relation of knot theory, except written for braids and proven in exactly the same way. So it's, I'll write it in a schematic form. It's the fact that if you have one fixed chord, then the sum of the two chord diagrams that you get by taking a point here and connecting it either to the left or to the right above is equal to the sum of the two chord diagrams that you get by to the negative of the sum of, the sum of this sum with plus this sum with negative signs is equal to 0. Maybe I should just write it in full. I don't know why I'm so lazy. So this plus this is equal to this plus that. So all of them have the same chord in the same place between the last two strands, and this has that plus that, and this one has this plus that. Okay? Sorry, I don't know why I was so lazy. Okay? So now, similarly, actually, so you can ask yourself, is there a homomorphic and co-homomorphic expansion for braids, so for pure braids, so for PB? And the answer is yes, but it is hard. Okay? It's a hard theorem. Anyway, now you can do the same for PWB. So for PWB, for PWB, it's actually even easier. So you can, so the augmentation ideal, so PWB again is the group generated by sigma ij modulo, actually I think I want to write all the relations this time. So the relations are sigma I, sigma j, minus sigma j, sigma I, sorry, not minus, is equal to sigma j, sigma I, if I minus j is greater. What am I doing? Sorry, I wrote some. These are not even elements of PWB. What I wrote. Sorry, I wanted to say the relations are sigma ij, sigma kl is equal to sigma kl, sigma ij. Sigma ij, sigma ik, sigma jk is equal to the same thing transposed, and this is really Reidemeister 3. And finally there is this overcrossings commute relation, which says that sigma ij, sigma ik, sigma jk is equal to sigma jk, sigma ik, and I remind you, all of these things mean something about flying rings in R3, but the algebraic relations at the end are these. Anyway, I becomes the ideal generated by things like sigma ij minus 1. So in the associated graded of, well, let me call this just the group so that I don't have to copy the name each time. In the associated graded, this becomes a generator. So you can look at the class of sigma ij minus 1 and call it, and it's an element of the associated graded. right? This modulo I squared is an element here. So let me call this element Aij. And then you can check that the associated graded in full is the algebra generated by Iij, by the Aij's, modulo relations that are immediately inherited from these relations. So these relations are the commutator of Aij with AKL is equal to 0. This comes from the first relation. Then the commutator of Ai k with a jk. No, wait, I wrote it wrong. No, it's wrong. Sorry, I wrote undercrossings commute instead of overcrossings commute. I'm sorry. Sorry, so this is a sigma ij, sigma ik is equal to sigma ik, sigma ij. Sorry, so here also the commutator of sigma ij with sigma ij, aij with aik is equal to 0. And then there is a relation which is inherited from Reidemeister 3, and it's a 4T relation, but I can write it in a completely algebraic form. So in a completely algebraic form, I write it as Aij plus Aik commutes with Ajk. So the commutator is equal to 0. And if you want to see what this relation looks like, then just interpret Aij as an arrow. So if this is 2, 4, then this is A2, 4. And if you interpret Aij as an arrow from number I to number j, and you write this and you expand this, it becomes the 4T relation. So this is just the same good old 4T relation. And then in the 2 minutes that I have left, I will tell you that there is an expansion. So the expansion z going from g into a of g. So all I need to tell you is where do the generators go. So it is defined by z of sigma ij is equal to the exponential of aij. And that's it. Okay? And you know, well, I don't have the time to verify that it's an expansion, but it is. And then the only, you know, if I had another few hours, I would tell you that this eventually leads to, so this becomes an invariant of W braids, which can be extended to usual braids, which then descends to an invariant of knots, and this is the so-called Alexander polynomial. Now there are many other ways to get to the Alexander polynomial, but I just wanted this way. Okay, so yeah, that's the end of what I have to say. So not see you again. I mean, see you again, but see you around, but not see you again in this class because the class is over. Okay, thank you for listening. Hello, Dinushi. Okay, I'll turn off the video.